Hey class, what's going on? I hope you're having a great February break. Today I'm going to go over number 1 from worksheet 8-5. This is an assignment you can find on the Google Classroom. All I want us to do is I'm just going to go over number 1. That's all I want us to do for this. I said I would do 1 and 2, but I'm just going to do number 1 with you because it covers basically everything that we need to know for gravity. All right, so we have all of our givens. We have our the mass of the moon. We have the radius of the moon. We have the distance between the Earth and the moon. That's the moon's orbit. We have the mass of the Earth. We have the radius of the Earth, and we have the radius of Earth's orbit. That's from the distance between the sun and the Earth. So that's that. All right. Now the first question says an astronaut is standing on the moon holding a feather. Calculate the acceleration due to gravity on the moon. So we are looking for g. We are looking for little g, that is. All right? Little g. Okay? We are looking for little g. Now, I haven't showed you this formula yet, but this is a new formula. I will be explaining it more in detail on Monday when we come back. But another way to get g, that's acceleration due to gravity. Little g is the acceleration due to gravity, is going to equal to big G, which is the universal gravitational constant, times the mass, the bigger of the masses. So that's the mass that's making the object fall, in this case the feather, making the mass. So it'll be the moon making the feather fall towards the moon, divided by the radius squared. All right? So we have little g equals gm over r squared. Looks very similar to every other formula that we've been doing. So we have all of our givens. We have the mass of the moon right here. We can use that. That's the mass of the moon. That's what's making the feather fall to the earth, is the mass of the moon, right? We have the radius of the moon, right? That's right there. Okay, that's the distance between the feather and the moon center, which is about 1.74 times 10 to the 6 meters. All right, and then we calculate for g. All right, so let's plug in all of our values. So this will be a. All right, so g is going to equal to our gravitational constant, which is 6.67 times 10 to the negative 11. I'm not going to be able to fit everything. Hold on 1 second. All right, hold on. I'll do a better job writing on here. All right, so let's do g is going to equal to our gravitational constant, which is 6.67 times 10 to the negative 11. Now we have to use the mass of the Earth, not the mass of the feather. The feather doesn't matter. The mass of the moon. Sorry about that. That's a correction. The mass of the moon, because the moon is making the feather fall. So it's negative 11 here, not negative whatever that looks like. So times 7.4 times 10 to the 22nd divided by the radius of the moon. Remember, we're on the moon here. Is going to be 1.74 times 10 to the 6th, and that has to be squared. All right, that's how you get the first one. All right, you just plug that into your calculator, and you should get the value, the answer, which is at the bottom or the back side of this page. All right, and it should come out to be around 1.6, I believe. G equals 1.6 meters per second squared. And that is your answer. That is part A. Alrighty? Let's go on to part B now. So part B says the astronaut drops the feather from a height of 2 meters. How long does it take the feather to hit the ground? Now this is a straight line kinematics problem. This is going way back to kinematics. So again, now we have our acceleration due to gravity. Our acceleration due to gravity on the moon is 1.6 meters per second squared. all right? And we know that it follows a height, a distance of 2 meters, okay? And it does that with an initial velocity of 0, a VI of 0, because we're dropping the feather, right? So this is going way back, all right, to straight line kinematics, all right? So we have our acceleration due to gravity, we have our distance, we have our initial velocity, and we are looking for the amount of time. How long does it take? So that's a time question. How long does it take for it to hit the ground? So time equals question mark. Time equals question mark. All right. So if you can reflect back on the equations that we used in straight line kinematics, the equation we end up going to is this one, where we have distance is equal to v initial y times the time. Hold on, I'm going to rewrite this. I'm not liking that. All right. So distance is equal to v initial times the time plus, now we used to use at squared over 2. Well, g is the acceleration due to gravity. So we can use g. It's the same thing. It's still an acceleration. It has the same unit as acceleration. So we gt squared over 2. Now our initial velocity is 0. So anything 0 times any number is 0. So the VIT cancels out, and that's 0. All right. And then we plug in everything. All right. So we have our distance is 2, is going to equal to our acceleration due to gravity, which is 1.6 times t squared over 2. All right. Now we have to solve that algebraically. All right. So we end up getting is time. I'm going to go up here because I have some space up there. We have time is going to equal to the square root. Everything's underneath the square root. 2 times 2, because you multiply the 2 to both sides. You multiply this 2 to both sides because it's on the denominator, so you multiply 2 to both sides, right? And then we're left with 2 times 2 equals 1.6 t squared, and then divide by 1.6. So we're going to divide this by 1.6. All right. So I pre-made the square root symbol because I knew we were trying to find t. We want t, not t squared. So I knew that we were going to ultimately be a square root, a whole thing. But that's not the first thing you should do. You first multiply 2 to both sides, divide by 1.6, and then you take the square root. I just looked ahead. I was able to understand what the next step was. So it's 2 times 2 divided by 1.6. And you should get a time of about 1.6 seconds also. So that's just a coincidence, all right? All right, so don't think too much about that number being similar to the acceleration due to gravity, but it comes out to be about 1.6 seconds, all right? And that's part B. All right, let's move on to part C now, all right? So part C, I'm going to erase all this here. Come on. All right, so let's move on to part C now, all right? Part C. Now, part C is a little bit trickier, all right? Part C, it says the feather has a weight of 0.020 newtons on Earth. Now, what is the same thing as weight? Do you remember? Do you remember what the same thing as weight is? Yes. If you're thinking force of gravity, it's the same as the force of gravity. So weight equals force of gravity. Now, the force of gravity is equal to mass times gravity. Now, we can do this when we know G. if we know G, we can do mass times gravity to get something's weight. All right, so since we do know G on the moon is 1.6, we can do mass times gravity. All right, but here, this is the issue. This is the weight of the feather on the Earth. So on Earth, the gravity has 9.8, not 1.6. So first, we have to figure out what is the mass of the feather. All right, because what do we know about mass? Mass stays the same everywhere. So we have to find the mass of the feather. All right, so we have to use the weight on Earth, the gravity of Earth, right? Because this is all on Earth, to get the mass. And mass stays the same wherever you are. It's the amount of matter that makes up an object. All right, now we're going to solve for m. Okay, so m is going to equal to the weight of the feather on Earth, the force of gravity of the feather on Earth, which is the 0.02. All right, so that's the force of gravity or weight of the feather on Earth. So it'd be 0.02 divided by the acceleration due to gravity on Earth. Now that's because we're on Earth, the acceleration due to gravity is 9.8. That's been the same since forever. All right. Now, when all is said and done, we get the mass being 0.002 kilograms. All right. That's our mass. Now the question is asking what is the weight on the moon? All right. So we can take that mass and multiply by the acceleration due to gravity on the moon. Right. So we know that the force of gravity, same equation, is equal to mass times gravity. Right. Now we're going to the moon. So this is where the gravitational pull of the moon is slightly different than on Earth. So we do 0.002 times 1.6, because that is the 1.6 is the acceleration due to gravity on the moon. And when all is said and done, we get a force of gravity of 3.3 times 10 to the negative 3 newtons. All right, and that would be the weight of the feather on the moon, about 3.3 times 10 to the negative 3 newtons. All right, so that's problem number 1. Hopefully that all makes sense to you guys, and we can get going again on Monday when we come back. We can continue working on this worksheet. We'll probably do number 2 together, and then I want you guys to try to do some problems on your own. So if you want to go ahead and try these other problems, go for it. It's not required. I am going to check to see that you guys watched this video and you did this problem. Hopefully it makes sense to you guys, and we'll see you Monday. Enjoy the rest of your break.